Multivariable Calculus, Section 11.3, the cross product. Grrr. What's a vector got to be angry about? Well, the cross product has nothing to do with anger. Recall that given vector v with these components and vector w with these components, we define the dot product this way, the product of the components then added together, and that resulted in a real number. But there's a second way to multiply vectors called the cross product. And that cross product creates a vector, not a real number. So we begin by defining the cross product in 3 dimensions as the determinant with ij and k along the first row, the first vector along components along the second row, and the components of the second vector on the bottom or third row. Now, in any determinant, there is a plus or minus sign associated with each element, always starting with a plus sign in the upper left-hand corner and then alternating down the columns and across the rows. And we evaluate a determinant by reducing it by minors, it's called. And what we do is we choose a row or a column and work across it. So I'm going to choose the first row. So I'm going to start with the first element, which would be plus I, and ignore its row and column. What's left creates a 2 by 2 determinant. Then I'm going to move along that first row because that's what I selected, and the second element in that first row is minus j, and ignoring its row and column creates another 2 by 2 determinant. So this way what we're doing is we're breaking down a larger determinant into smaller determinants. And then finally the last element in that first row is plus k, and when I ignore its row and column we have another 2 by 2 determinant. Now hopefully you remember how to evaluate a 2 by 2 determinant. If not, I'll review that. You take the upper left-hand element times the lower right-hand element and then subtract the product of the lower left-hand element times the upper right-hand element. And so we get I times V2 times W3 minus W2 times V3, and then continuing that in the second one, the second 2 by 2 determinant, you get V1 times W3 minus W1 times V3, and so on. And so this is one way to evaluate the cross product. You can write this formula down or memorize it, but actually nobody ever breaks down a 3 by 3 by minors because there's a shortcut. For the shortcut, what we do is we take that determinant and we copy the first 2 columns. And then we multiply down the diagonals, so that would become V2 W3 times I, and then the next diagonal gives you V3 times W1J, and then the third diagonal going downward gives you V1 W2K. Then we multiply up the diagonals, so that gives us W1 V2K, the next diagonal W2 V3I, and finally W3 V1J. And then what we do is we take the bottom vector minus the top vector. And what happens then is we get the same formula that we got on the previous slide when we broke the determinant down by minors. Now, this shortcut only works for a 3 by 3. If in the future you may have larger determinants, they have to be broken down by minors. But the process is the same as what I showed on the previous slide. Here's an example with numbers. Let's find the cross product of these 2 vectors. So there's our initial determinant by definition. You put ijk on the top, v along the second row, and w along the third row. Copy the first 2 columns and multiply. That's 0i, negative 3j, negative 4k. Then the other diagonals upward, no k, 2i, 0j, and then it's the bottom minus the top. So for I, we're taking 0 minus 2. Now they're not in the same position, so you have to be careful. And for j, it's negative 3 minus 0, and for k, it's negative 4 minus 0. And so we get this vector at the right there as the cross product. Now there are some interesting things to talk about. Here's the same example, but this time we're going to do w cross v. Before on the previous slide we did v cross w. So this time w takes the middle row and v takes the bottom row. Again, we copy the first 2 columns, we do our diagonal multiplications, I won't belabor that. And there we have the top and the bottom. So again, you take the bottom minus the top. So for example, for I we've got 2 minus 0, and for j we've got 0 minus -3, and so on. And this should look familiar. It's exactly the same as the previous slide, except for the minus signs. So it turns out that W cross V is the opposite of V cross W. And you can prove this with the formula or with the components, but it's just tedious, so we won't be proving these things. All right, here's the same example again, same original vectors, and what I want to do is show you a picture of what's going on. The blue vector is W, and the red vector is V. Let's call W cross V R. Okay, so there's what R looks like, pretty much to scale. Notice that if we dot R with V, we get 0. And if we dot R with W, we get 0. What does that mean? Do you remember from the previous section that if the dot product is 0, the cosine is 0, and therefore the angles between R and each of the other two vectors are both 90 degrees. This always happens with cross product. And again, you can prove it, but it's very tedious. You break it down with components and so on. So we won't bother with that either. Just remember that the cross product is a vector perpendicular to both of the original vectors. Now, in addition, geometrically, if you think of a screw, if we cross W with V, then you draw an arrow from W to V. Now, if you turn the screw in that direction, which is counterclockwise, what happens? It comes out of the hole. And so the vector W cross V comes upward, just like the screw would. I'm not kidding you. This is how you figure it out. Now, what if we do it the other way around? Then we get the opposite, right? So if we go from V to cross W, V cross W in that order, now we're going to be turning the screw clockwise. Well, what happens to a screw when you turn it clockwise? Well, it goes down into the hole. And so the V cross W goes downward. And so if you're working geometrically, this is how you can figure out the direction of your cross product. Now, another theorem in your book is that the length of the cross product is equal to the lengths of the two original vectors times the sine of the angle in between. And this is extremely tedious to prove, so we won't do that. They sort of half prove it in the book if you want to look at it, and mention that the other half you use components and multiply it all out and you get a big mess, but it eventually works out. So we'll just use this. So here are two vectors, and there's the angle in between. And they determine a parallelogram, as shown. And if we drop a perpendicular, what's the length of that perpendicular? We're just using simple trig. You should be able to figure out that that's the length of the hypotenuse times the sine of theta, which in this case would be the length of vector W times sine of theta. And so the area of this parallelogram is base times height, which is the length of V times the height. Well, that's just, according to the formula above, the length of the cross product. So here's another interesting fact about the cross product. The length of a cross product is numerically equivalent to the area of the parallelogram determined by the two original vectors. That's kind of interesting. So if two vectors determine a parallelogram, then three vectors are going to determine a solid. So let's draw the parallelogram determined by A and C, and then the parallelogram determined by B and C. And if we continue to draw parallelograms parallel to these, we get a solid, which is called a parallelepiped. You can think of it as sort of a squashed Kleenex box where the angles are no longer 90 degrees. And if I shade it in, you can see it a little better. Now we're going to figure out the volume of this parallelepiped, and we'll use the bottom, which is parallel to the yellow top, as our base. And the area of the base then is the length of the cross product C cross B. And the reason I'm using C cross B instead of B cross C is because C cross B would be coming up out of the parallelepiped, whereas B cross C would go down. And it's going to look better on the picture. Now to get the height of the parallelepiped, we draw this right triangle by extending the top of the front face. And then theta is the angle in between the line segment that's the height of the parallelepiped and vector A. So the height is just the length of A times cosine theta, because the height is the adjacent leg in that right triangle. So now we have the volume, which is just the product of the base times the height, the area of the base times the height. Now here's the interesting part. If we draw C cross B, it's perpendicular to the base. We've shown that before. And so it runs along parallel to the height. And so the angle theta is actually the angle in between these two vectors, C cross B and vector A. Therefore, what we have up here for the volume is in fact the dot product of the two vectors. And so we can rewrite our volume formula as the cross product of the vectors in the base dotted with the other vector. Now, because the choice of the base was arbitrary, we could have chosen any of the faces of the parallelepiped for our base, and therefore the juxtaposition of these letters is irrelevant, and we can rearrange them any way we want. So for example, B dotted with A cross C would also give the volume of the parallelepiped. Now, we have to have absolute value, because occasionally, depending on how we cross product, we could end up with a negative value. The cross product of two vectors dotted with a third vector, called a triple product, is the volume of the parallelepiped determined by the three vectors. Okay, here's an example from the text, type of exercises you're going to have to do. Compute A cross B, and we've already done one, but we'll do this one too, because the numbers are a little bigger. There's our determinant. Notice that A takes the middle row and B takes the bottom row. We recopy the first two columns, and then we multiply diagonally 10i, negative 4j, negative 20k, and then up the other way, 4k, 10i, 20j, and then it's bottom minus top. And so you take 10 minus 10 for the i's, negative 4 minus 20 for the j's, and negative 20 minus 4 for the k's. Simplifying, you get your answer. Now remember, this vector is perpendicular to the two original vectors, and its length is the area of the parallelogram determined by A and B. Number 14. Find the area of the triangle with vertices P110, Q101, and R011. So let's take a look at where those points are. Notice that P is on the xy plane, Q is on the xz plane, and R is on the yz plane. Now if we take a vector RQ and a vector RP and cross them, then the length of the cross product is going to be the area of this parallelogram, and so the area of the triangle will be half of that. Okay? So RQ, we take the Q numbers and subtract the R numbers. So we've got 1 minus 0, 0 minus 1, and 1 minus 1. Then for RP, we take the P numbers minus the R numbers. So that's 1 minus 0, 1 minus 1, and 0 minus 1. So then I'm going to cross those two, and I didn't show the work, but if you take the cross product, you do get 1, 1, 1. Some of you have a feature on your calculator that'll do the cross product for you. Aren't you lucky ones? So then the length of that vector is the square root of 1 squared plus 1 squared plus 1 squared, which is root 3. Now that's the area of the parallelogram, and so the area of the triangle then is root 3 over 2. Number 16. Find the volume of the parallelepiped with edges OP, OQ, OR, given the points P, Q, and R the same as in problem number 14. Now O always stands for the origin. So what we're talking about are these three vectors with the same numbers as the points. Now you can cross any two of them and then dot with the third, but there's actually a quick way to do it all at once, and it doesn't matter how you line it up because you're going to take the absolute value anyway. So B dot A cross C, B would be in the first row technically, and A and C in the next two rows. But again, you can put these vectors in any row you want. The only difference will be sometimes it'll come out negative. All right, so that determinant is -2, and again I did it on scratch paper. And so the volume then wouldn't be -2, obviously. It would be +2 cubic units. Number 20. Determine if the following 4 points are coplanar. There's A, there's B, there's C, and there's D with ridiculously big numbers. If so, if they are in the same plane, then the parallelepiped created by any vectors in the plane would be completely flat and therefore have 0 volume. So what we're going to do is compute these 3 vectors, and again you can use any combinations, and then compute the volume of the parallelepiped, and if it turns out to be 0, then we know the points are coplanar, and if not, they're not coplanar. So there's AB, there's AC, and there's AD. So our determinant looks like this. Now those numbers are awfully big. I don't really want to do that by hand. So let's take a look at how we would do it on the calculator. Okay, to evaluate this determinant in our calculator, we put it in as if it's a matrix. So I go over to Edit, and I've already typed the numbers in. See, there they are. And then we quit out of there. And then we go back to matrix and go over to math, and determinant is the first one in my menu, so I select that. Then I go back to matrix, and I typed it into A, so I select A. I don't really need the parentheses. And so the determinant, the value of this determinant is in fact 0. So the calculator gave us 0, and that means that yes, indeed, the 4 points are coplanar. And now it's your turn again to work some problems. Have fun!